Here we go. Slideshow. Okay. Now, guys, you know, we talked about this last year in reinforced concrete. The only design method that is recognized by the National Building Code is the limit state design. Okay. And like I said, limit state design is a design method. It's not related to any type of material. It's just the way that you actually accommodate the required strength and serviceability for whatever you want to, build. So that's what limit state design is. And so a design approach to provide adequate resistance for strength. Okay, and then you'll see this ultimate limit state. That's for the strength. And then they call it SLS, serviceability limit states. Now, last year we did very little on serviceability. We went to the table, we made sure that we hit the table to make sure that the beam was stiff enough. But with steel and wood, we will check the serviceability when it comes to deflections. And so we will be checking both. The only thing I haven't done is I haven't included vibrations in serviceability, and I'll tell you why. And, depending on the spans that you guys are working with, sometimes vibration is not an issue, especially if you keep the deflections with what we call acceptable deflection. That also tends to control the vibration. So we'll talk about that more in due course. Now, strength limit state calls, refers to the maximum load carrying capacity, overturning, sliding, and fracture of a structure. Okay, so keep in mind that we have never done any lateral, overturning, sliding, but if ever you get it, we are going to be doing some lateral forces both in the steel project and in the wood project. So we'll get to see that. And yes.
Do you think you can mute everyone, because I hear like some background noise and I don't know what it is?
Oh, yeah, that's something that I'm going to mute all. Let me just mute everybody. Everybody, keep your cameras on, but mute yourself, and then when you want to come back in, just unmute yourself. Anyways, okay. Okay, so please mute yourselves. Okay. Now, so overturning and sliding, of course, is something that if you're designing a retaining wall, you have to make sure your retaining wall is overturned and slide out of place. Okay. And of course, a fraction of the structure, that's where you get fatigue. Fatigue basically applies for bridges where there's a lot of vibrations. If your structure is going to have a lot of machinery and cause a lot of vibrations, that can cause fatigue. So these are all things that you have to take into consideration. Okay? So ultimate limit states is to make sure it's strong enough. And then, of course, serviceability limit states are those that restrict the normal use and occupancy of the strength, such as excessive deflections. Because you don't want to all of a sudden have everything just sag and start making things crack, especially if it's things that are susceptible to cracking or at least supported by the structure. You don't want to have excessive vibrations. In other words, you don't want somebody sitting at the kitchen table and then all of a sudden, as you walk across the floor, you start bouncing up and down this chair. We have permanent deformations. When it comes to steel, that's not necessarily an issue because steel doesn't have a lot of creep, but wood can have some issues with permanent deformation, and I'll show you how you can control that with wood. Okay? And then, of course, local structural damage. In other words, you want to minimize the cracking that these serviceability issues can cause. People get very upset when you buy a building, you start seeing cracks in the ceilings, on the floor, and so on. Okay? So now, when it comes to loads, remember there's three categories of loads within the safety design. Okay? One is called loads that are, so loads are the forces, are the enclosed force and pressure applied to the building structure. Where the load is, we a force, in other words, concentrated load, or pressure in ounces per foot or kilopascals. Now, yes.
Sorry to interrupt you. I don't know if it's only me, or your voice is not like really clear.
Oh,
yeah, it's me too.
Yeah, the audio quality is a bit low.
Yeah, I don't know. Maybe it's the mic, or maybe there's like an where you're sitting. There's like some sort of an echo. I cannot like explain it clearly, but it's not clear.
Is it clear now?
It's just the room. You need to get like something that's sound dampened. like
Like,
blankets or something.
Last semester it was perfect, like we could hear you really well the whole time, but today there's some noise, or maybe this is what Reina was talking about, like I don't know, but it's
Okay, so you hear vibration, right?
kind of, like I don't know how to explain it, but it's really kind of.
Well, I thought that by using the microphones it would help. At least it doesn't help. Is it clear now, Norman?
It's very much the same, I think.
Very much the same. Okay.
Yeah.
So you're saying that there's a lot of vibrations.
Yeah, it's like if there was a background noise.
And there's a lot. And there's a lot of background noise at the same time.
You're in the can.
Okay. Well, look, I'll try to fix the glitch for next Zoom. For now, I'm just going to continue. Is that okay with everybody?
And especially when you start like talking a bit fast, I lost the track of your words completely.
Okay. Okay. Well, if you want, Norman, I can put the subtitle on these PowerPoint presentations. We're gonna.
When like with the recording, there's like some sort of subtitle, but sometimes it's not like it cannot like detect the exact words.
Well, it's pretty good. I tested it. I can do it with the PowerPoint.
Okay, as you wish, but maybe just for the future. I don't know.
Let me try it now. How's that, Norman? Okay, hold on. You'll be able to see the subtitles. Norman, you see?
Wow, yeah.
Okay, I mean, I can do that. I don't know if it would be distracting, you understand? But like I was planning to do that, but I wasn't sure if it's going to be distracting or if it's going to help.
It's like an international movie now.
Exactly. I can speak Italian and the shit translated in English.
Exactly, yeah.
So is that better, Norman, with the subtitles?
Yeah, maybe for today, yes.
Okay. I apologize.
No, it's okay. Thank you.
Okay, so listen. Okay, so the force and pulls and the forces. Okay. Now, we were here. Okay, so the permanent loads, of course, those are the dead loads. Those are the loads that are being carried permanently by the structure and, of course, the weight unit itself, any material that's covering, and machinery, so on and so on. And as far as permanent loads, that's what we found in the National Building Code. And I don't know if it was covered properly in your structural analysis class. I do go into this into a lot of detail in structural analysis. Then, of course, variable loads is a load that frequently changes, okay, magnitude, direction, location. So therefore, a variable load would be, of course, the live load. Of course, it can stand in one place in the room, it can stand somewhere else. It can be 3 people, it can be 30 people. And same thing with your snow load, okay? You can have 12 inches one day, 6 inches another day, and you can start accumulating. And of course, the wind load, it can come from any direction and so on and so forth. So your 3 variable loads, of course, are your live load, or your occupancy load, your snow load, and your wind load. And then, of course, we don't get into this, but the rare loads are these are the earthquake loads. Okay, and that's, of course, the one scope of this program. And however, Montreal is in an earthquake zone, and you have to decide which is the form of government, is the wind load or the earthquake. For steel structures, very rarely is it the earthquake load, even for wood structure. Sometimes the wind load will govern the earthquake to be a ice structure. When it comes to reinforced concrete structures, guaranteed that the earthquake load will always govern the wind. So those are the loads. Now, of course, the type of loads and effects to be considered your dead load, and of course, the capital D will always represent dead loads. And then you have your earthquake loads, capital D, and then you have your H, the permanent load due to lateral earth pressures, including groundwater, of course, that is something that has to be evaluated. I did the last class in reinforced concrete last year. Unfortunately, only 5 of you came. I did some of this lateral load, sure, that's not a topic there. And of course, the wide load, of course, the variable load is going to be played when you're designing a room, and depending on what the room is, you'll have a minimum variable load that you have to apply. And permanent effects caused by pre-stressing, they're, we're not going to be getting any pre-stress concrete or whatever impact pre-stress. We don't have to worry about that. That's all in itself considered. And of course, the snow load is something that we will be doing for both projects. And temperature effects, okay? So temperature effects due to contraction, expansion, deflection caused by temperature changes, okay? Shrinkage, moisture changes, creep, and ground cells. Now, when it comes to wood, wood is is a very natural material, and it does have problems with shrinkage changes. So that's something that's going to have to be considered depending on where it's being placed and so on and so on. Okay? Temperature changes. Well, if you're building inside of a building where you can be making sure that's well insulated and the temperature is very, very, very little for the time it's built, the time it's going to be used throughout the whole season, you don't have to worry about temperature changes. Shrinkage in wood is something that is to consider. I'll give you examples of what happens when you don't take into consideration the shrinkage of the wood. And of course, creep is what they call inelastic deformation of sustained loads. And creep is very, very, very predominant in concrete, not in steel. In wood, it has a built effect. Of course, ground settlement will hopefully in your soils class. So these are the loads that you always have to consider when you're designing the structure. And then of course we're going to be primarily considering the dead load, the small load, the wide load, and of course the last one, the wind. Okay, we will consider wind, wood project and steel project, and we'll be incorporating that in the design for the walls and so on. Okay.
Sir?
Yes.
Can you go over what creep is again?
Creep is called inelastic deformation due to sustained loads. Okay. Now that's the technical definition of creep. What happens is that, especially reinforced concrete, when it's being after it's in place, just the self-weight of the structure itself to sustain load, let alone whatever is going to be put on top of it. Okay. With time, it will start deflecting. Okay. Just even if you don't put a light load on it, it's going to deflect under its own weight. I don't know if you guys remember walking down on the E-wing, the corridors. If you ever really notice it, if you look at the floor, you'll see that there's little valleys in the floor. Okay, after you go back a little time, you can go back to the office and see this last year. But what happens is that with time, the concrete tends to deflect. Not because it's being overloaded, and this deflection will actually be permanent. It will not recover itself. You can recover creep, but most of it will stay inelastic. So that's one of the things about reinforced concrete that you have to be concerned about. Things do creep, and especially, for example, in reinforced concrete, when you have a hundred-story building, well, the columns on the ground floor, it can creep quite a bit. Okay, so people that are designing the ground floor, that type of structure, will always keep in mind. And how do you overcome it? You make sure that whatever non-structural element is going to be below it, you leave a gap. There's ways of compensating for creep, but you just have to remember that concrete does creep a lot. Wood will creep also. If you ever walk into an old building, then you look at the floor, you see that the floor has a little bit of a sag in it. Well, that's caused by creeping. And so there are, and wood is not as bad. Like I said, steel, you don't have to worry about creep. Now, we're not going to be doing any creeping calculations, but in reinforced concrete, if you're going to be designing something, that's one of the effects that has to be kept in mind. And I have when I design my structure. At the same time, you can compensate for whatever creep is going to happen by making sure that materials don't get affected by creeping. Okay? So, now, Okay, now remember, okay, when you're designing a limit state design, that you have to design according to importance factors. Okay, you have IS for snow, IW for wind, and IA for the earthquake. We'll talk about this one. And of course, here are the importance factors for snow, for wind, and we'll talk about earthquake. So when it comes to snow, I personally, I never regard this. I can be completely barred from my calculation. I never worry about load. Okay? A building that represents low hazard to human life and event of failure. In other words, if you're designing a barn, you can use those importance factors. Okay? And I don't even bother. Some people do, and I don't. And then, of course, most of our, like in our situation, housing and office buildings and so on, they fall in the normal, so the importance factor is 1. And of course, you get into schools and so on, the importance factor is 1.5. And then if you get to post disaster, like for example, fire stations, police stations, whatever, you know that you have to increase all your variable loads by 25%. What I want you to note here, okay, is that look, like for strength, you except for this one, okay, for strength you tend to increase the forces to make sure they're resisting that. Then when it comes to serviceability, they don't change. You see that? They don't change. So therefore, as a matter of fact, you will lower your force for serviceability instead of increasing it. Now, nobody wants to know why all of a sudden you're lowering your force when it comes to serviceability.
Yes, sir. I would like to know.
Okay. What happened with
I'd also, sir, I'd like to know, why does it stay the same throughout no matter what category it is for serviceability?
Why does it stay the same? Because it's basically just your specified load. Okay, your specified load is what you're going to be using to check serviceability, and you're going to see this in the example we're going to be doing for both wood and steel. So it'll be a little clearer when we do the example. Okay, but why does it go down? Why does it go down? Why is it the same? Because when it comes to checking for deflection, for vibrations, for whatever, it's the load that you're actually going to intend to subject your structure to that's going to govern how much of it is going to deflect under that load. Okay. Now, the reason why they came up with 0.9 here, okay, as opposed to, in my days, this was 1.0, this was 1.0, like these are all ones, okay, for snow. But what happened was that I don't remember if it was 2005 or 2000 or 2005. All the climatic information on the National Building Code, okay, they used to use all the climatic information based on the probability between 1 and 30 years. So in other words, you had, okay, and then they changed that to 1 and 50 years. So in other words, they went to a wider period for the information regarding the snow loads and wind loads and all that. So it increased the forces that you would get regarding the snow load, and therefore it made the building a little stronger. But then when it came to serviceability, they realized that it wasn't really necessary to worry about that additional load. So they kind of reduced the values back to 1 in 30 for serviceability, and that's where they came up with these values here. And then for wind, the same thing. The wind, they reduced it even more for the wind. So that's why. So they kind of like upped it for resistance in the climatic information, and then when it came to serviceability, they kind of brought it back to what it was back into it. And then they left that 0.9 and they did the 9 and they came up with these values. So that's where, and of course, I see this because I've been practicing for 40 years, and you kind of ask myself, oh, they had it there and then they took it away there. Kind of makes sense. That's why. So, anyways, I just want to make you understand why these things are smaller, because they went back to using the actual loads that you would find in the probably that don't appear. So if you take a climatic information from the 1985 building code, you take the one from the 2015 building code, and if you multiply 1 by 2015 by 29, probably the snow load that we see used back in 1985. Here, all drawings.
Sir,
Yes.
I'm sorry to bring that up again. I think you're not using the mic on your speaker. I think you're using the mic inside your laptop. Can you go to the mute button? Beside it, there is a slide up. You can choose the mic from there.
Okay. Okay. I think that's what's happening. How's that now?
Yeah. Now it's better. Yeah.
Oh, it's so
Wow.
much clearer.
Perfect.
Yes,
It's
perfect.
Wow.
Yeah,
Thank
good.
Such
you.
a big difference.
Wow!
very
Wow! Yeah, it's because thank you, Omar. I thought I had.
Yeah, big time.
Sorry, I apologize. I thought I had made that setting, and I thank you for reminding me, Omar. I knew exactly where he asked me to go. Thank you, Omar. How's that,
No
guys?
problem.
Better?
I
Yes,
hear you
yes,
properly.
yeah.
I can actually understand what you're
Fantastic.
saying.
That's like
Can we start it from the beginning?
So, pardon?
Can we start from the beginning?
No.
No.
No? Oh.
No, I mean, unless, well, what time is it now? Well, we've already, well, look, if the video is not clear, the video should be clear. If the video is not clear, I'll be more than happy to.
This is a review though, right?
Okay.
Pardon? Yeah, this is more like
Yeah.
we saw this last year, and
We don't need to
unfortunately,
go over this.
yeah, we saw this last year, and unfortunately, I'm gonna have to repeat this again in steel. So you guys are gonna hear it in steel because I have more people in steel. So the ones that aren't in the wood class, they're gonna have to hear this. You understand? And so.
All right, there we go. We're fine.
There you go. So Nermin, you're going to hear it 3 times. Once last year, badly today, and hopefully well on Monday. How's that?
No, the more the merrier. It's okay.
Sounds good to me, guys. Sounds good. Okay, so thank you, Omar, again, okay? Okay, so here you go. Now, remember this. See, isn't this fun? Like it's starting to be a bit of a repeat, right? Load combinations. Do you guys remember this a bit? No? Okay, the effects of principal and companion loads is determined, okay, with this table before. So therefore, this is like, I hate they use the word case here. This is not a case, this is a combination, okay? Like, and they put case 1, case 2, because when we're gonna be doing the steel project, you'll see we'll have different combination, but we'll also have different load cases, okay? So I find that the wording here is really bad, okay? So bear with me. I don't like to use this because people say, well, if that's a case and that's the case, what makes a difference? No, these are load combinations. So here they put combination, they should have used combination 1. Anyway, I just copied this straight out of the wood book, okay? So if you remember, like when you only have the dead load, the load factor is 1.4. And don't worry about this. This here is only for overturning and for sliding that you reduce your dead load. So we won't be using this unless we're doing some overturning or some sliding, and we won't be doing that at all in this, okay? So we are looking at 1.25 the dead load, 1.5 the live load. And then if you happen to have snow load that accompanies your live load, in other words, you can have, for example, I have an example here, and we'll go through it, where, for example, on one side of the lintel, there's a room, and on the other side there's a roof. So you're going to have both snow, and therefore you're going to have to decide, okay? And I'll show you how, on the example, I'll show you how to combine these. So in other words, this is when your live load is a principal load, and the snow and the wind are companion loads. And then this is when the snow load is the principal load, and then this becomes the companion loads. And then of course, this is when the wind load, and we're going to be doing this, especially in the wood project, okay? We're going to be using this equation, okay? And then of course, this we won't talk about at all, okay? So now, and this year, last year, I think I don't think we did any of these last year, but this year we'll be doing all 4 of these, okay? Either in the program or on the project, we'll be touching all of 4 of these, so you guys will get a little bit more comfortable how to do these load combinations, okay? Not load cases. And oh, let me just clear this drawing here. Okay, so now now for serviceability, okay, this is what's nice about it. For serviceability, of course, all of these factors end up being 1. Okay, so in other words, what they're saying, the effect and the principal companion loads is determined by using the combination, okay? So so all of these become 1. In other words, whatever specified load that you have, Okay, whatever specified load that you have, that's the value. You don't turn it into a design load. For serviceability, we use a specified loads. In other words, if I'm using 2.4 kPa for my live load, that's what I use for my serviceability. If I'm using 1 kPa for my dead load, that's what I use for my serviceability. Now, if you happen to be in a serviceability with a companion load, here you can see that this gets reduced to half. Okay, so in other words, you put your live load and only half your snow load. You put your snow load and only half your live load. Now, this changed in 2015, okay? In the past, these also used to be half. That's also changed. Like sometimes it scares me when they make these changes and I ask myself, shit, what I designed in 2003, is it really under designed according to these new requirements, you know? And that's why, guys, I keep telling you, whatever the code tells you to do, of course, it's a law, it's enforced, you have to respect it, but it's the minimum. It's up to you to judge if you want to use that minimum, because if something goes wrong, you're still responsible, okay? So don't feel uncomfortable. You know, yes, it's good to optimize, but if you feel that you need to put a little bit more, put more. Let your client pay for it and sleep at night, okay? Anyways, when we get into the wood, I'll tell you some horror stories I have now. Like, thank God they demolished the building, because if you look at, anyways, we'll talk about that in the wood. Okay, so guys, like I said, this is for serviceability. All they're saying here is to make sure you use the specified load for serviceability, and you'll see that in the examples we're going to be doing in this course in both wood and steel. Okay, now here, of course, this here, okay, so we have a lintel. I showed you this example last year, but what I did this year is I actually reworked the example point by point, because I didn't like the way it was done last year. So the lintel supporting a roof and a floor of a school, okay? So basically here, okay, so that you guys can, okay, the lintel has a span of 3 meters. So that means I have a column there, I have in plan view, and this is the lintel right here. The lintel is simply a beam that goes across an opening. It could be a window, it can be a door, whatever. So there's my lintel. Now they say that the tributary width of the roof is 3 meters. This is stupid. 3, 3, 3 is very confusing. So that means that if this is the roof on this side, here's a roof. So that means there could be some kind of supporting member here. That means that these members here are supporting at least 6 meters away in order for the tributary width to be only 3 meters here. And on this side, there's some other kind of bearing supporting member here. And the floor also has a tributary width of 3 meters. Okay, so this is the floor. And of course, another 3 meters here. So therefore, that's what they're saying. So in other words, all the load on this side will get transferred to the beam. All the load on this side will get transferred to the beam. And that's what they will repeat tributary widths again. Okay. Now they're saying that the specified dead load for the roof is 1 kPa. That's what the roof weighs. And then for the floor, 1.5 kPa, which is reasonable for a school. And then here the snow load, the ground snow load factor is 1.8. The associated rain is 1.2. And here they're telling you that CB is 0.8. That means it's not a big thing. CW for a school, you have no choice but to use 1. You can't even use anything lower than 1. It's a flat roof, so your CS is 1, and there's nothing that's going to cause any type of different shapes. You can assume that it's going to be a regular snow load over blanketing the whole roof, so therefore your shape factor is 1.0. And of course, the National Building Code requires that a minimum 1 kPa, so in other words, in the summertime, if you have 2.4 kPa here, you still have to assume that there's a 1 kPa here that can be used if the workers have to go in there and maintain the roof. So that's for, you know, so if ever you get a snow load and you do your calculation, you happen to have something less than 1 kPa, in other words, 20 pounds per square foot, you should be using at least 20 pounds per square foot, 1 kPa. Okay, and of course, the specified live load for a school, this comes right out of the National Building Code. This is 50 pounds per square foot. So that's the information, okay, that we have. And now let me just clear this drawing. And of course, so now, so here the unified specified dead load. And now guys, when I put a small w, that means it's a uniformly distributed load, okay? And the subscript D stands for dead load. In other words, I haven't factored it. So basically, if you want to calculate the unified, because basically what you're doing is you're going to be designing a beam and you're going to want to know what's the uniformly distributed load that's across the beam like this with a span of 3 meters. So therefore, you have to convert everything into kilonewtons per meter in order for you to be able to analyze and design your beam. okay? This should all come back with the examples we're going to be doing. So don't worry about it. Here is just to show you how to use the different combinations when one is a principal load and one is a companion load. So you guys can get a gist of what's happening. So here, basically, you take your WD, okay, 1 kilonewton per square meter times 3 meters. This is for this was for the roof, and this was for the floor, and therefore the total dead load here is 7.5 kilonewtons. Okay. Now, the unified specified load W is the live load times the tributary width again, always. So you take your pressures, your loads, in other words, your kPAs, you multiply them by your tributary widths, and it transforms them into a uniformly distributed load on the member you want to design. Therefore, the 7.2. Now, the snow load, of course, you have to do the calculation, and I'm sure you guys all remember this equation, right? Just kidding. Okay, so the snow load is calculated by the importance factor of your structure times the ground snow load times all these factors plus the associated rain. And of course here, because it's a school, the importance factor is 1.5. And of course here, this was the ground snow load of 1.8. And then of course the associated rain, this comes out to 1 kPa. And of course now you want to transfer that into a uniformly specified snow load S. So I like to use a subscript, L for my live load, S for my snow load, D for my dead load, so I know what I'm looking at. And I guess, and when I put these letters, they're just specified loads. They're not factored. Now, when I'm going to factor them, okay, so now the uniform for the, oh yeah, for the live load, this is when there's no snow, you're just looking at the live load, is 1 kPa times 3. So now I've got all my uniformly distributed loads. Now, this is my load combination 1. Now you'll notice that all of a sudden I use WF here. WF means that it's factored, and therefore these become my design loads. This is what I'm going to be using to do my analysis to calculate whatever force I need to calculate in my member. So now in this case, I only have dead load, therefore the load factor is 1.4, okay? Now, load combination 2, where you have your dead load and your live load, but now your snow load, you don't have any wind. Your snow load is a companion load, so therefore that one you only have to multiply by 1.5. So therefore you take 1.25 times your dead load, 1.5 times the snow load, and then you add, of course, just you don't factor the live load, you don't factor snow load, and then this becomes WF for load combination number 2. And then load combination number 3 is the other way around. The snow is the principal load. The live load or the occupancy load is a companion load. Therefore, you just like they get the load factors get switched from 1.5 down to 1 again. And like I said, in 2000, 2005, this used to be 0.5. Okay, so now they've increased it by 50%. And of course, I get here 25.08. There's not much of a difference, but this is still a little bit higher. Then, of course, there's another combination where you just consider the live load, okay? So therefore, you have 1.25 your dead load, because your dead is always going to be there, okay? It's just depending the combinations of your variable loads. And of course, 1.25 your live loads, the one that's on the floor as well as on the roof. You check that one also. You get 24.68. And of course, you look at 1, 2, 3, 4. You always design for the highest one, and therefore, of course, that's the one that governs, and that's the one I would do my analysis with. In other words, get my moments, get my shears, and design my lintels, and then after that, have it properly designed for the forces that I've just calculated.
Sir?
Yes.
Your last one looks exactly like the second one, just without the snow load. Would that ever govern over the second one?
Believe it or not, David, before they changed this from 0.5 to 1, okay? You understand what I'm saying? Like 2005, if you go look at the 2005 National Building Code and you look at the load combinations, for load combination number 2, this is 1.25 your dead load, 1.5 your live load, and this is 0.5 your snow load in the 2005, okay? And then in the 2015, they changed this to 1. And in 2005, believe it or not, this is the one that used to govern the design. You follow?
I mean, I understand that it used to be different, but I can't see how adding a number would make it smaller. I can understand the 0.5 would make that smaller.
Yeah.
But I still feel like that's an extra 0.5 to snow load.
No, but if you, in other words, if you do this calculation where you put 0.5 here instead of this will become smaller.
Yeah.
0.5 times this will become smaller. And in my days, this is the one that governed the design. In other words, that was the highest one. See here, this is just the live load on the floor and the live load that you're putting on the roof of 1 kPa and 2.4 kPa. Here, there's no companion load, it's just live load. Because see, here, when the snow load is there, I don't consider the live load on the roof of 1 kPa. But when
Okay.
You understand?
Hit me. Yeah, it just hit me. Understood now. Okay.
Now it clicked, right? In other words,
it just clicked when you said that. Thank you.
Okay, so like, in other words, this is for winter conditions, this is for summer conditions. Make sense now?
Yes, thank you.
Okay, so I'm glad you asked that question. And like I said, if I would do this according to the way I've been designing for the last 40 years, this is the one that would govern my design. So there you go. Anyways, that's why I got gray hair, guys. It's not because I'm getting old. I'm getting nervous. Just kidding. Okay, so now serviceability, okay? Now we'll talk about serviceability. What we'll be talking principally concerned about will not be vibrations. And like I said, vibrations become an issue when you start spanning, like in steel, when you start getting to 10-meter spans and you're using very light structure, you can have a vibration issue. In wood, when you start exceeding, well, what's 16 feet? About 4.5 meters, it can become an issue. So vibration become issues when you start getting to long spans and you don't take that into consideration, and vibration could be an issue. But if your spans are relatively short and if you're not using, for example, very light steel, normally vibrations do not become an issue, but deflections should always be checked, okay? Because that, no matter what, the span should always be checked. So now, adequate bending stiffness shall be provided so that the maximum deflection, and of course, when we talk about deflection, they use the Greek letter delta of a member that does not exceed the values in the following table. Now, guys, don't panic, okay? We are going to be using this table. Now, what I want to stress here, this is something that you have to keep in mind, okay? Is that this here, total load, and we'll be doing this in an example, so don't worry about this. The total load, okay? The deflection criteria, delta max, is L over 180. L is equal to the span of the member you're checking. And of course, the 180 is just a constant, okay? Now, so here, what they're saying, when it comes to wood, this is not an option. This is required, okay? In other words, you have to check this and make sure that you satisfy this condition. And we will be doing this in the examples, so don't worry about it. Now here, what I don't like about this table is that when it comes to, for example, floors here, we're going to be doing this live load deflection, suggested L over 360, okay? L over 3 suggested. Yeah, it's suggested in the standard, but then when you go to the National Building Code, L over 360 is required, okay? And then I'll tell you when you should be using L over 360, okay? So we'll be doing a couple of examples, so don't worry about that. So all I want you to get from this table is that this one is required by the wood code, okay? Because this is the standard for wood. CSA, this is not a 0, this is CSA 086, okay? So this is a CSA standard that we're gonna be using. You won't see it, but this is the one that we're gonna be using that the handbook is based on. All the tables are based on this, okay? And in this standard, they want you to make sure you satisfy this criteria. And as well, the National Building Code wants you to satisfy this criteria. So we're gonna check this, we're gonna check this. We'll see which one that governs. If the one that governs, we satisfy, will automatically satisfy both, okay? So we will be doing this in the examples, so don't worry about that. All I want you to realize here is that when you see like delta max, okay, is equal to L over 180, okay? So in other words, this is the maximum deflection you can have. So for example, if I have 1,800 meter span, okay, over 180, that means the maximum deflection that this thing can have is 10 millimeters. That's what it means. So that's the maximum deflection. So I take the span divided by this constant, and it tells me what is the maximum sag that this member can experience under the loads that I'm designing for. So like I said, we'll be doing this quite a bit. We'll be doing both for steel and for wood. So you'll get very familiar with this. Don't worry about it. And Any questions on this? Like I said, like what I want to stress is that this is required, okay? But wood, not steel, okay? This is suggested here in wood, but not in the National Building Code. You might as well put required, you understand? So anyways, I find that a little, sometimes I find that the way that things are written, very, very, very misleading, okay? Okay, so here we go. So that's serviceability. Now, I'm going to show you how to apply, of course, okay? Okay, so if we want to do the serviceability combinations that we were doing in the other example, of course, this doesn't change. All I'm doing now, okay, so in other words, this still stays the same. In other words, the dead load from the roof and the floor stays the same. The live load from the floor stays the same. The live load from the roof stays the same. But what happens to the snow load? Okay, well, if you remember, okay, when it comes to the snow load, if you remember SLS, I don't want to go back. I should maybe put a hyperlink. This used to be 1.15. I don't know if you guys remember that. Okay, the importance factor for strength was 1.15, but for serviceability is 0.9. So the snow load actually became slightly smaller now for serviceability. You see, as opposed to, I don't remember what, I think it was 1.56 before. I don't remember. But all I'm saying is that, so this is where the importance factor comes in. So if you're doing snow or wind, well, and then especially for wind, we're going to be doing this in the wood class, okay, 0.75, and we're going to be using that when we're doing serviceability. So I'll remind you about this again. And hold on a second. Where's the whatchamacallit? Where's the clear to drawing? Sorry. Okay. So that's where, you know, that load combination varies because, and then of course, now the snow load dropped from whatever it was before down to 4.44. And of course, now this is only when you want to check that first condition where L over 180, in other words, you're taking both the dead load and the variable loads combined at the same time. So that's the only time you use L over 180. So therefore, and of course, in this case, the span of the lintel was 3,000 millimeters. That means over 180, this thing can actually sag 16.5 millimeters, which is not bad, you know, over a 10-foot span. I mean, that's a lot, trust me. Okay, and now for load combination 1, of course, you only take the dead load. Okay, so it's 1 point. So therefore, you see that now the load factor becomes 1. That doesn't change. And then for load combination 2, it's all 1, except now you take only half the snow load. Okay, so therefore, you take this. And then for load combination 3, which is, of course, the snow load is the principal load, you take the full snow load, and then you only take half the live load. Okay, and then of course, and then the load combination do only the live loads. So therefore, you're going to combine the dead load and the live load on the roof. I'm sorry, on the floor and on the roof, you get 17.7. And then here, all of a sudden, the one that will govern your design, of course, is this one. Okay. So what does that mean? That means that if I, for example, have my beam here, okay, this is my beam. I take the highest. So here I'm going to apply a load on here, okay. I'm sorry, this shouldn't be WF. This is, I'm sorry, I apologize for this. This is when you paste and cut. This should just be, this should be W, guys. I apologize for that, okay. This is wrong. I'm going to correct that before too late. This is wrong. It should be W. So W here, okay, is equal to 17.7 kilonewtons per meter. And therefore, how do you calculate the deflection of a simply supported beam? It's 5W 5WL to the 4th over 384 EI, okay? So therefore, you just, you know, 5, this is your W here, the span here is 3,000, so you put 5 times this, You take the modulus elasticity of your material, you take the moment of inertia, and that's going to give you the deflection. And if this deflection is greater than that, then your beam is no good. Then you're gonna have to go resize your beam. And we'll be doing these calculations in the example, so don't worry about it. Now, this is just for when you put in the total load. Now, when you put in just the variable loads, well, it's slightly different. The variable loads, you completely disregard the dead load. But the problem with that is now your L, instead of being 180 here, when you're looking only at a variable, the L jumps up to 360. So in other words, yes, you have less of a load, but you have a smaller deflection that you're allowed to have under that smaller load, okay? So we'll be checking for both, like I said, and therefore here you do just the live load and snow load. And then here you do the, I should take off the subscript, I apologize. And then I take off the, and then of course, so out of these three, this is the one that governs, and therefore I would be checking my deflection based on this load, because if it's good for this, and that's how you do it for serviceability. And I, like I said, I apologize for the Fs. This is just a cut and paste, and I forgot to take off the subscripts. So I bear. Okay, now, any questions, guys? Like I said, we'll be doing this in examples. It's just to, if ever you guys want to go over this, if there's nothing that's clear, please, at any time. Okay, like David did before, he wasn't sure, and then it finally clicked, and sometimes that's all it takes. It's like, instead of it becoming an issue, you get that aha moment, and that's important, you know. And sometimes it happens at 2 o'clock in the morning. Okay, so now, I just want to talk about, like, this week, I'm only going to talk about one type of wood that we use. Sorry, clear all drawing, okay. Does everybody know what plywood is?
Yes, sir.
Okay, so we all know what plywood is. Who doesn't know what plywood is? By all means, don't be shy. I mean, okay, so we all know what plywood is. Okay, so plywood panels are built in sheets of softwood veneer glued together with a waterproof resin adhesive. Okay, now, of course, that used to be the old days. Now they got poplar plywood, so it's no longer just a softwood. And just for you guys, so that I found this on the internet, I found this to be kind of cute. Okay, so basically this shows you a little bit of, like, you know, it's not very, very picturesque, but it gives you an idea that, you know, they take the log, you know, they strip the bark off the log. And then what they're doing here, that they're cutting the log in certain lengths. And then they take the log and they soak it in this tank of water. Okay, they soak it. And then after that, they've got a machine that shaves, like this thing turns around and the machine shaves this little thin piece of wood. Now this little thin piece of wood is called a veneer. Okay, so these are veneers. And then, so this is what they do, is they actually, like, in other words, they'll just shave the wood, and these veneers are about 1/8 of an inch thick. Okay. And then it goes to an optical scanner, it looks for defects. And then, of course, this machine cuts the veneer, and then this machine dries it. And then here, this machine kind of lays the veneer in one direction, lays the veneer in the other direction, lays the veneer in one direction. So in other words, plywood always has the veneers in a 90-degree, you know, direction, one from each other. And then after that, it gets stacked. It goes through a hot press. Okay, it goes into a hot press. The whole thing gets glued together. And then, of course, it comes out, it gets sawed to the right size, it gets sanded. Sometimes it gets sanded, like this is if you want to sand it, if otherwise it doesn't go sanded, and off to the lumberyard, ready to be, you know, sold and installed on your project. So this is a very quick process of how, you know, plywood is made. I hope, you know, gives you a little bit of a better idea what happens. And of course, now, you know that plywood, typical plywood size is 4 feet by 8 feet. Did you guys know that?
Yes.
Okay. Now, what happens because of this plywood size? What does that impose on your structure?
So what do you mean by impose?
In other words, what does that force you to do when you're building a wood structure?
You might want to try to make your building in 4 by 8. Like, for example, you want to do things 12 feet wide.
No, not necessarily. You're trying to save plywood. No, that's not what I'm getting at. But it's a good. I like that. I like that idea. That would be really optimized, David. That would be really good. But
in case you don't have like a saw or something, I don't know.
Yeah. In other words, you don't have a saw. You can't cut off the ends. And no, but that would be a plus, David. The thing about these plywood sizes, what they tend to do, okay, they tend to govern how you're going to be spacing the members that are going to be supporting the plywood. Do you follow what I'm saying? Okay. So for example, if you have a floor, normally you're going to have floor joists. Okay. Now, when you put your floor joists down, you just don't randomly pick, I'm going to put them at 14 inches, or I'm going to put them at 18 inches, or I'm going to put them at 22 inches, okay? What you're going to do is you're going to take a multiple of 12, of 4, I should say. So in other words, what these panel sizes kind of impose how you're going to be spacing your supporting members, okay? So the supporting members are typically placed at like 12 inches, 16 inches, because 16 is a multiple of 48. This used to be, this is not done very frequently, but you can also go to 19.2. In other words, this is a multiple of 8 feet, okay? 19.2 inches. So this one, like if ever you go into an old building and all of a sudden you're banging on the wall and you drive a nail at 12 inches, and then you drive one at 16 inches and you can't find the stud, and you drive one at 24 inches, well, it's possible that they put the studs at 19.2 inches, okay? Because that, if you take 8 feet and you put them at 19.2 inches, you can get even space members, but that's very rare. We use that today, okay? So the most typical spacing we have is 12 inches, 16 inches, and 24 inches. So this way, when I have my sheet here of 4 feet by 8 feet, and I have here, for example, one member, okay? And therefore, if I put them at every 16 inches, I'll have another member here, I'll have another member there, another member there. And then when it comes to the edge, the other member is going to fall right on a supporting member. So that's why we tend to use these multiples, okay? So therefore, the plywood, when it goes down, the edge of the plywood sits on a supporting member, and the other edge of the plywood sits on a supporting member. So that's why so these are typical spacings that we use when we want to frame lumber. And of course, that's why we use 12 inches on center, 16 inches on center, and 24 inches on center. Now, so on floors, this is the typical spacing, 16. But then if for whatever reason you have a heavy loads and you don't want to get into some, you can also come down to 12, okay? Very rarely we will space the floor joist at 24 inches. 24 inches normally applies for roof structures where we tend to space the trusses or whatever rafters we want to do on the roof. That's where the 24 inches is very, very common. And like I said, so very rarely do we put 24 inches for floor. So this is more for floors here, okay, and walls, okay, and this is more for roofs, okay. And this, like I said, it is an old dimension. I've seen it once in my life, so I'm not saying it's never been done, but very rarely this is done. So these are the more typical ones. So this, and that's what, and it's because of the sheeting material. They're all made in 4 feet by 8 foot panels, okay, and therefore that's what dictates the spacing of the supporting members. Now, hopefully one day these Americans will become metric, and we will go down to a beautiful 1200 by 2400 sheet of plywood, and therefore the spacing will be 300, 400, and 600. So today we say 300, but we really mean 12 inches. We say 400, we really mean 16 inches. And when we say 600, we really mean 24 inches. So it's just a soft conversion, okay? We don't say space at 610, we say space at 600, and the guy's gonna space them at 24. But one day when everything becomes metric, well, the 300 will be 300, the 400 will be 400, and the 24 inch will be 600. So whenever, hopefully you'll see it in your lifetime. Okay, so that's it. So that's what's the thing about paneling. And of course, we are going to be definitely always using either 12. Like I said, we're going to be using 300, 400, or 600. And of course, that's like 12. When I say that, keep in mind it's going to be 12 inches, 16 inches, or 24 inches, because that's what is the actual spacing for these panels, okay? Now, the other thing is that keep in mind that plywood comes in certain thicknesses, okay? And of course, here the thicknesses are in millimeters. I don't know anything in millimeters. I know all my thicknesses in inches, okay? Like I have, like I know, I usually use 3/8 of an inch plywood, 1/2 inch plywood, 5/8 of an inch plywood, and I use 3/4 of an inch plywood. So for me, it's all still imperial in my head. But these are the, very equivalent metric for 1/2 inch plywood. I think this is, I forgot what this is, but the most typical plywoods you'll find is this one here. This is 3/8. this is 1/2 inch, this is 5/8, and this is 3/4. So these are the typical ones that you find in the lumber yards, okay? And of course, when they get sanded, they become a little bit thinner, okay? So these are the ones that you use for framing. In other words, when you want to create a floor, a wall sheeting, or whatever. Okay, so these are the ones that we're going to be looking at. And like I said, for me, this is 3/8 of an inch. This is 1/2 inch, and this is 5/8, and that's 3/4, which is 19 millimeters. So that these are the ones.
Sir,
Yes, yes.
One more question. What's the exponent next to the numbers when you go down the table?
Well, number 4, available as square edge or easy tongue and groove. Okay.
Those are for the notes. Okay, thank you.
Okay, so like these are the footnotes. And like I said, now that you brought it up, does everybody know what tongue and groove is?
The malfamel? No, it's kind of not that. Sorry, it's just when there's a little slit in the middle of the plywood that you can connect them in.
Yeah, well, that's it. Like when you're ordering plywood, you can either have a square edge, which is what most of them come in. Okay, square edge means that this is a cross section. Okay, this is a cross section of the plywood. Okay, so this is the square edge. In other words, it's just square. You can have plywood that has tongue and groove. In other words, one side has a tongue on one side, and then on the other side of the panel, I'm going to make it, of course, there's a groove, okay? So this way, when you put one beside the other, the whole edge is supported here, because usually your member would be sitting here, your joist would be sitting here. So in other words, if I'm looking in plan view, okay, let me change color so you guys can see this. If I'm looking in plan view, if I have a floor joist here, I have a floor joist here, a floor joist here. So normally we put our panels so that our panels end up halfway on this floor joist here like this, right? So in other words, this is all supported, but then this edge here is not supported, and this is where the tongue is here. I'll change, let me put a green. So the tongue is right here, okay? And then when you put the next one, so when I put the next piece here next to it, this whole edge is supported between the supports. And that's what they mean, supported edge. So you can have tongue and groove, or you can have square edge. So when you're specifying a subfloor in your house, you would always specify, for example, 5/8 of an inch tongue and groove plywood, so that the edges are all supported. And this way it's going to minimize any damage that it's going to have on your flooring. So that's what tongue and groove is, okay? Easy tongue and groove profiling. So, clear drawing. Okay, so that's it. So number 4, anyways. Okay, any questions so far? Now, another type of paneling that's very popular in wood framing, okay, is OSB. You guys heard about OSB, oriented strand boards? Well,
yes.
oriented strand boards are structurally matte formatted panels made of thin strands of wafers sliced from small diameter round trees and bonded with exterior under heat pressures. Now, just so that you guys can refresh your memories, I found this picture, which I think would be pretty good. Okay, so this is an oriented strand board. Everybody sees that? Okay, so you can use this. I hate OSB boards personally, okay? I mean, they are cheaper to buy, it's cheaper to, like people like this. I never was a strong oriented strand board person. I like plywood, and I'll give you my reasons one day, but you can see that, of course, and this is what I was telling you about before, you understand? So these, everybody recognize these are called engineering joists, okay? So here in the engineering joists, even the web members are made with OSB boards, okay? And this is what I mean by making sure that, like, in other words, here you can see that the spacing is 16 inches, 1, 2, 3, 4. In other words, this is 4 feet, and look, see how they stagger the joints between the panels. So they'll have one joint here, they'll go 4 feet. So therefore, and then of course, so the joints are always staggered. They should be staggered when you're doing a flooring, and so on. And like I said, so here at the bottom, you can see what when they say wafer board, that means there's absolutely no orientation. They just put all the chips together, they squish them together, they press them, and they come up with a panel. So that's a wafer board. That's what you see down here. Then of course you have where the core is actually, put in, like perpendicular to the outside face. In other words, it might not look like it's oriented, but if you look at the long strips, most of them seem to be going in a certain direction. And that's what they mean by oriented strand boards. So here they always put the long direction on both outside faces, and then in between they'll put them perpendicular. Okay, so I think this is called OS2 because okay, and then the inside can be random. So of course this is much stronger than this one. Okay, and of course this one's a little bit more expensive than that one. So you can have totally random, which they call a wafer board. I think this is called OS2 and this is called OS1. Okay, I'm not sure. Don't take my word for it, but I know that there's OS2 and I think they're going to stop making wafer boards altogether for some reason. They're just going to be having. So this is, so this is how the strands are actually placed. And it might not look, but they are somewhat oriented in a certain direction. So that's the OSB, okay? And anybody have any questions? Guys, if I show you a picture of something that strikes you, just let me know and we'll discuss it, okay? Okay, so last viewed. Now, of course, the same thing as a plywood. They're 4x8, and therefore the spacing requirements for OSB board would be the same as for plywood. In other words, now here are the imperial sizes and the metric sizes: 3/4, 9/16. Okay. What I find interesting is that there's no 1/2 inch in OSB. 7/16 is the closest thing you can get to 1/2 inch, which is close enough. 1/16 of an inch is not much, and there's no 3/4 of an inch either. So I find that's very interesting. So now we'll talk about these markings on the next slide. So don't worry about this. This is something you should be familiar with, okay? But this is what you really have to realize, is that the thicknesses are something that you should remember, like 3/8, close to 1/2 inch, and so on. So don't look for 3/4 of an inch OSB board. You don't have any. These are the thicknesses, and of course, you can see that what they did when it came to OSB, they came up with nice metric values, and then they kind of made very fractional values in imperial, which is a start, you understand? So this way, when it eventually all goes metric, this will be completely gone, and all you're going to be seeing is this here, okay? So the panel size of 4x8, okay, cut to size. Yeah, you can, of course, like even plywood, guys. If you want to have plywood, you can get plywood in bigger sheets, but they have to be special orders, and same thing with OSB. But of course, you'll be paying the price. So this, now we'll talk about these markings here. This is something you should be familiar with, okay? Now, the performance markings, okay? The CSA standard 023 construction sheeting sets performance markings for specified end use as for floors, roofs, and wall sheeting. So basically, and this applies both for plywood and for oriented strand board. Now, I know this is jogging your memory, but if you go back in your spec class, I don't know if you did it with me, but in the spec class, in the last lab, you did the last one was on wood, and there you had markings that you had to specify. You probably did it without realizing what you were doing, and this will give you a better understanding of what you're doing, okay? So basically, the F stands for floor, the R stands for roof, and the W stands for wall. So keep in mind that sheeting, plywood can either be placed on the floor, can be placed on the wall, can be placed on the roof, okay? So that's what the letter stands for. So depending where you're placing it. 1 and 2, okay? 1 means that the edge is not supported. In other words, okay, that means that if I have my joist like this, and I put my plywood across here like this, okay? This edge here is not supported, okay? So that's what the 1 stands for. Now, if I use a tongue and groove plywood, then the edge is supported and it becomes a 2, okay? So 1 is unsupported edge, 2 is supported. Now, on a roof, it's important, okay? So you can have 1R, that means you're not supporting the plywood over a 2-foot span, or you can have a 2R where you're supporting the edge. Now, how do you support the edge? You can use tongue and groove plywood, you can use H clips, you can put blocking in between. As long as your edge is supported, it's considered a 2, okay? And of course, for wall, it makes no difference because it's vertical. It doesn't make a difference whether the edge is supported or not. So that's what the F stands for. Is it a floor? Is it a roof? Or is it a wall? is the edge supported, non-supported, or supported? That's what that stands for. Let me just clear this. Now, 16 is the spacing of your stud. Okay, so 1F16 means that you're going to have a floor, your members are spaced at 16 inches on center, and the edge that is running perpendicular to your joist is non-supported. Okay, of course, this is 20, this is the 19.2. Okay, this is the 24. Okay, so the one unsupported floor spaced at 24 inches. Very rarely do we do this. Very rarely do we do this. Okay, so just to let you know. And of course, subfloor with panel type underlay. Now, just so that you guys, hold on a second. I'm sure that I found, what is an underlay? Well, an underlay is what you lay under the floor finish, not underneath the plywood. So in other words, okay, so if you look here, okay, this here, these panels here are your subfloor. In other words, that's your structural element. That's what's actually supporting your floor. And these panels here are underlays. These are the ones that you put on top of your subfloor so that you can put your floor finish. Okay, because there's certain, like these panels that you buy to do the subfloor, they can be very rough. In other words, they can be they can have a lot of holes in them and whatever. And you can have a very, very soft floor finish that eventually it will just follow the deformations of your subfloor plywood. So in order to avoid that, people like to specify an underlay so that they have a better finish paneling on which they will be applying the finish. Okay, sometimes the underlay could be made out of plywood over plywood. Okay, in other words, a better finished plywood, like a sanded plywood over plywood. So in other words, here's your subfloor, and this is a plywood underlay. Sometimes the underlay can be a sheet of cork because you want to do some soundproofing. Sometimes it can be like there are many types of underlays. Okay, it's not just wood. But so the underlay is a nice finished panel that you will be putting over your subfloor so that you can put your floor finishes that are very susceptible to deformations. Like you can have vinyl floors that are very, very sensitive to, how deformed the subfloor is. Okay, and of course, carpets and so on. Normally, like if you have a hardwood floor, I wouldn't even bother with an underlay, but carpet, vinyl floors, and ceramics, definitely you would have an underlay because you want to have a very rigid buildup so the ceramic doesn't crack. That's why you would have an underlay for ceramic, but not necessarily because you're afraid that the deformations are going to affect how the ceramic is going to behave over time. So so in other words, this is structural, this is non-structural, okay, and of course, like I said, and that's, yes.
What is cork?
Sorry?
What's cork?
Cork? Do you ever open up a wine bottle?
Yeah.
That's cork. They can make, you understand? In other words, it's a very soft bark, right? That they put as an underlay sometimes to give us acoustical values to the floor, okay?
Can I put that in the walls?
No, on the floor. They use it as an underlay. You can have.
I know, but you said it's like a soundproof, right?
Well, it's soundproofing, but on the wall you might as well use insulation. It's cheaper.
Oh, okay.
You follow? So yeah, like I'm not saying you can't use it, but there are materials like I'm not going to put a bad insulation underneath as an underlay. It won't work because it's going to be too soft, right?
No, but if you really want the room to be like soundproof, you could put the insulation and then put like a cork over it.
If you want, yeah. The more you put, the better it is going to be. The more expensive it is. Everything is limited by how much money you want to spend or your client wants to spend. You understand?
All right, perfect. Thank you.
Okay, so so that's what I mean by like these underlays. Anyways, they're different. All I'm saying is that don't have this preconceived idea that the underlay is only plywood. No, the plywood is one of the more typical underlays, a finished plywood, but you can have other, like if you ever go on Google, just put in floor underlays, you see all of the other different materials that you can use as an underlay, okay?
And sir,
yes.
You said before when you would put hardwood, you wouldn't put an underlay, meaning no plywood at all, and just on the
subfloor, just right on the, no.
Not the rafters, sorry.
On the subfloor, yeah. Especially if it's 3/4 of an inch plywood, hardwood. You understand?
Okay, so you'd staple it directly on.
Pardon?
You would staple them directly on.
Yeah, exactly. Because like a 3/4 inch hardwood, there's no need to have an underlay for a 3/4 inch hardwood. You understand?
Yeah.
Okay. But a ceramic, I would definitely have 2 sheets of plywood because ceramic is very susceptible to deflection, and therefore, if you put a very, like if you happen to The reason why I would say you put 2 sheets of ceramics, okay, because here, let me just show you. Because when you have ceramics, like let's say, for example, you have my mother stepping right here, okay? She's a very heavy lady, you understand? And she steps right there. Guess what's gonna happen to your ceramic? If you only have 1 sheet, there's a good chance it could crack. Or let's say you have a big piece of furniture that's sitting between the 2 joists and it happens to create a very excessive deflection. It's going to crack your ceramic. So by having a stiffer floor, it's going to minimize your floor from cracking, because ceramic is very, very sensitive. And of course, the bigger the ceramic, the more sensitive it is going to be. In other words, if you have these people, oh, I want to use 3 feet by 3 foot ceramics. Whoa, on a hardwood floor, I'm saying on a wooden structure, I would be very, very cautious of how stiff the floor should be so that it doesn't crack on you. You understand? So keep that in mind, because that's what I said. That's where all the question of serviceability comes in. You understand? And you better make sure that you stay within those deflection limits. Otherwise, the ceramic will crack, the drywall will crack. See, for example, this is a good example here. So for example, here, okay, let's say the person decides to put drywall underneath this floor, attached to the floor, right? Okay. So this is where, for example, if the drywall is attached to this floor, and if I'm looking at it in this direction, so here's my joist, okay? If my drywall is attached, to here, I should have used a different color, sorry. If my drywall is attached here, okay? So if these things sag excessively, okay, in other words, if this sags excessively, deflection, okay, what do you think is going to happen to the drywall? It's going to crack. Okay, so therefore, that's why you have to minimize the amount of deflection that's going to occur, and therefore, we're going to make sure that the thing is stiff enough so that this does not exceed, the deflection here does not exceed the span divided by 360. And we'll be doing that in our calculations, okay? So that's what they mean, material susceptible to cracking. You can have the drywall attached to the underside of your floor, and therefore, you're going to have to make sure that the deflection of the floor stays within a certain limit. Okay, so clear all the drawings, and I think that's pretty much last viewed. Okay, like I said, so these are the markings. I mean, they're very easy to understand if once you understand the the rationale behind it. The real thing that you have to remember is not the floor, roof, wall is the 1 or the 2. The 16 is the spacing of your members and all that. Okay, and of course, what this means is that if you look at a panel and they say 2F16, that means that you should not be spacing the things more than 16 inches. It limits the spacing of your members, okay? Now here is tables that we're going to take this table right away and we're going to design, for example, the subfloor for our project. We won't even break our head, okay? So here on this table here, okay, it has both plywood and OSB, okay? And here it says that, okay, the minimum required panel thickness. So if you have a load of 2.4 kPa on your floor, this is your service load, not factored, okay? If you're using, now DFP and CFP, okay? We will talk about this next week, okay? This is Douglas fir plywood, this is Canadian softwood plywood. Douglas fir is a species of wood, Canadian softwood plywood is all the other species of wood, okay? Because Douglas fir is a very, very strong wood and therefore it has, stronger mechanical properties. So if you have a load of 2.4 kPa and if your floor spacing is at 16 inches, then a 5/8 inch plywood would be ample to support that load. And that's how simple it is, okay? So this is for floors, and therefore, as far as we're concerned, we know that in a residential, I'm gonna go over this, the live load is 1.9 kPa. That's what you design a residential for, and we'll do this in the lab. And therefore, what I'm going to be specifying for the floor in our project, since if the spacing is going to be 400, and even if it's less, I'll be specifying a 5/8 inch plywood, and of course I'm going to put T&G tongue and groove so that the edges are supported. Okay. Now here, if you have a 4.8 load, in other words, 100 pounds per square foot, isn't this amazing? You can still use the same thickness of plywood for this spacing, okay, except for this one, which I would never use. First of all, I think this is ridiculous, and you'll understand next week why. I never bother with this, okay? And of course, so here is the plywood thicknesses that you would use for a floor. Okay, so they're saying don't use 1/2 inch for a floor. Use at least 5/8 of an inch. Okay, and of course here it just confirms that if my joist spacing does not exceed 16 inches, and we won't exceed 16 inches for our floor, and our floor load does not exceed 2.4 kPa, it won't. It's 1.9. Therefore, 5/8 of an inch is ample to support our floor. Now, when it comes to roofs, well, let me clear this drawing. When it comes to roofs, the next one has roofs on it. Okay, so if ever you're designing a roof, okay, depending on your snow load, okay, so here you have, okay, minimum required thicknesses or marking for specified for 2.0 kPa. Well, in Montreal, the snow load usually comes out to about 2.5 kPa, so this is no good for us. We should be looking at something higher. So in other words, minimum required thickness for 4 kP. Okay, so this happens to be the area of the snow load that we're going to be looking at. So we're looking at something. So this is the table that we should be looking at. Okay. Okay. Now, normally when it comes to roofs, you should support the edge. Okay, the edge should be supported. So therefore, I'm not even going to look at this. And when I'm saying supporting the edge, you can like, if these are my trusses, okay, in between. I don't know if you guys, did you cover this in construction one, H clips? Does anybody know what a H clip is? Did they talk about H clips anywhere in this program?
I think very briefly, like not a lot.
We might need
It
a
sounds
reminder.
familiar, but I don't remember whatsoever.
Yeah.
Yeah, well, they look like H's. That's why they're called H clips, okay? They're little aluminum clips like this. You see like a H, okay? And then what happens is that this is the H clip, and basically what happens is that the plywood slips in here, like in here, and then the plywood slips in here, like in here, and therefore this edge becomes supported by this little clip. Okay, so I mean, we can Google it after, and we can all go take a look at it. But if you're really curious, H clips are the cheapest way that you can have a supported edge. Okay, that's the cheapest way for a roof. The second way, you can put blocking in between. Okay, like in other words, a piece of 2x4 in between your trusses. And of course, the third way is having the tongue and groove. So therefore, in our case, okay, we're going to be using, okay, plywood, okay, and of course, the spacing of the roof trusses are always at 2 feet. Okay, so therefore the minimum thickness of plywood we'll be using for our roof is 1/2 inch. Okay, I do not recommend ever to use 3/8 of an inch for a roof. Okay, always use 1/2 inch, and therefore we know that 1/2 inch plywood is ample to support 4 kPa, and the snow load in Montreal does not exceed. So our floor is going to be 5/8 of an inch right here. That's for our floor, and for our roof, we're going to be using 1/2 inch plywood. Okay, and if ever you need to come back, you'll of course. I think I already sent you this lecture on Leah. So that's so you use the tables to select the thickness of your plywood. And then when in the very last course in wood, we're going to be doing some form work, and there's a whole different table just for plywood for form work, and then we'll worry about that at the end of the semester. Okay, I think overall clear drawings. I think that's it for today. Yeah. So let me just stop the recording, or stop. I'm going to pause the recording. Stop sharing. I'm going to pause the recording. Okay, so in theory, we should keep going. Okay, now we'll talk about the lab, and I'll slideshow from beginning. Okay, so lab number 1. So this is the, excuse me. Does everybody see the project on their screen?
Yes.
Okay, so guys, here I put the students will design and draw. I want you to, you can use AutoCAD or you can use Rivet. When it comes to wood structures, I don't recommend you use Rivet. It's a little bit, I find it's a little tedious. For the steel, you might want to use Rivet. I put AutoCAD, but you can use both, whatever you want, okay? Now, the students will design and draw Rivet, okay? Like we will, okay, now the house will be built in Montreal, National Building Code, and of course, this is the standard, okay? And then at the end, you're supposed to submit a design brief and a set of drawings, okay, on the last day of the semester, okay? So that's when it's due. Now, this here is a typical one-story house, okay? And if you see, what's going to happen is that we are literally going to be designing every element of this house. Okay, we're going to be designing the floor, we're going to be designing the beams, we're going to be designing the columns, we're going to be designing the exterior walls, we're going to be designing the lintels over the windows, we're going to be designing the whole truss, we're going to be designing the joints of the truss, we're literally going to be designing the whole thing, okay? So this is, you know, little house, and of course, here is there's the back elevation of the house, that's the front elevation, so you can see that, okay? Now here's a floor plan, okay? And of course, this is what you get from the architect. In other words, the architect sends you the outside dimension, tells you where the rooms are, okay? And basically what happens here is in this type of a structure, let me just annotate something here, okay? Okay, so in this case here, okay, normally what the way it's done is that, you know, you would have to design the floor, you know, like where you have to decide, we're going to do this today, we're going to decide where the floor is, and then all of a sudden, so therefore the floor gets designed, and then normally in this type of house, what happens is that the roof trusses will literally span and be supported only by the outside walls here, like this. Okay, so therefore these are all non-loading partitions. They will not be supporting the roof at all. The roof truss will be supported from here to here. Okay, so that's how we're going to be designing the roof truss. Okay, and of course we'll have to design these lintels, and we'll have to design the columns and everything else. But of course I will show you how to do that completely. So that's what we're going to be doing. And like 1 year, what I did is I started with the roof truss and worked my way down, because that's how you normally design a structure, but it doesn't work very well. It didn't follow the textbook. I don't ask you to buy guys to buy the textbook anymore. I find that the price has become ridiculous. It's over $200. So I don't ask you, but if you do want to buy the textbook, since you're a student, you can go to Canadian Wood Council. Okay, and you can see how much they sell for students. So this is the floor plan here, okay? Now, I only give you 2 dimensions, and don't worry about it. People say, well, how big are these windows? Well, what we'll do is when we get there, we'll use a graphical scale and we'll work out a dimension. So don't worry about that. And of course, here, so this is the floor plan. Of course, here's a fireplace, da, da, da. Now this would be the truss configuration that we're, okay, and what we'll do is we'll analyze this truss, we'll, you know, put the loads, we'll analyze this truss, we'll analyze it with ADA, get all the forces, and then we'll be able to design the web members, the top chord, the bottom chord. And then the second to last class, we will actually design each joint in this truss. So we will literally be designing the whole thing from A to Z. So this way, if you guys ever want to build a small country house somewhere for your parents, you should be, in theory, normally these trusses would be ordered from a truss manufacturer, okay, instead of you having, but if you don't want to spend the money or order those trusses and you actually want to make them yourself, you'll be able to actually design the whole truss. So that's the, you know, an overview of what the project's like. And now this is, yes.
Sorry to interrupt. So we're following that plan there, like that you said the architect would give us, right?
Yeah, the architect would send that plan and he would say, okay, put the wood structure for this house for me.
Okay.
So he would want to know, like, what are going to be the size of the joists, what they're going to space that, what will be the size of the beam, what's going to be the size of the columns, what are going to be the size of the lintels, the truss, and so on and so on. So this is everything that you would have to design. Okay.
Okay. Perfect.
Okay. Now here, what I did last year is I had, like, last year somebody had asked me. Oh, sorry. I'm back to this thing here. Okay. Oh, sorry. This is what I wanted to get to. I forgot to click. Now, last year, students were asking me, sir, what is it that I have to hand in my design brief? Okay, so this is going to be an outline of what I expect you guys to do. And as a matter of fact, you're going to start from today, okay? You're going to put everything on a sheet of paper. Okay, you're going to put everything on a sheet of paper. And basically, okay, so the design brief is basically, a design brief is a very fancy way of saying all your calculations. Okay, a design brief must, all the calculation for all the component lists below. And I want the document that you're going to send me. In other words, you're going to scan it, you're going to send it, and I want it in this order. If it's not in this order, you'll lose marks. I'll tell you right now, okay? Now, in other words, you're going to have 9 different headings. So for example, if you're doing heading number 1, you put that on a page. If you happen to get to half a page, that's it. That's heading number 1. Then you go, if you're going to do the floor joist, and even though you got room below on the next page, I want you to jump to a second page. In other words, when you're scanning, you're going to scan, by heading, not by pages. So I expect you to put, so at the top of the page, you can put geometry, dead loads for the ground floor. The live load is of course 1.9. And that's what we're going to be doing today. And then the week after, we're going to start designing the floor joists. And then after that, we're going to design the built-up beams. And then we're going to design the built-up columns. And then we're going to be sizing the footings. But I'm going to walk, I'm not just going to throw you into the deep end. We're going to be doing this, and I'm going to walk you through it. Like the lecture next week, we'll show you how to design floor joists. And then once we finish the lecture, you will have to design the floor joist for your project, okay? And at the same time, there will be assignments that I will be giving you that will prepare you for the exams. And as far as the assignments go, it's good for you, just like you did in concrete, it's good for you to do them. I will review the assignments at the very beginning of the lecture if I hand an assignment, and it's good for you to start practicing and getting ready for the test, okay? So here we go. And then of course for this, we have to do all of this. So this is just so I don't want somebody to come back to me at the end of the year and say, sir, I don't know exactly what to hand in for my design brief. It's all here. Just follow this step by step, okay? And this tells you exactly what I expect you to hand in by the end of the semester. And then by the end of the semester, you'll also have done drawing S1, S2, S3, F4, and then don't worry, I will give you typical examples of what S1 is, what S2 is, what S3 is, and what S4 is. So don't worry about that right now, okay? But this gives you, this is a, how do they say in French, aide de mémoire. In other words, this is going to help you to remember exactly what you're going to be handing in by the end of the year. And of course, this document is being slowly done throughout, from lab to lab, okay? So that's,
Sir,
yes.
Do you have this in steel too?
Yeah, I have one for steel also, yeah, why?
Okay, that's awesome. Okay, cool.
That I didn't send the one for steel, right? No.
Yeah, you did.
No.
No, I think I just sent the course outline for steel. I didn't send this yet. Or did I send the project? Anyway, I can go to Leah and check. But look, if I'm going to check Monday morning, or I'll check tomorrow morning, and if I didn't do it, you're definitely going to get it before.
Yeah, you sent the project.
In steel, I sent it also? Yeah?
Yeah.
Okay, great. So it's already done. Okay, so, and then we'll talk about the steel project in the steel class, okay? Okay, so this is just like I said, this is your outline, okay, of what you're going to be putting together. And now let's talk about, let me close this. Yeah, close that. Okay, so now here, okay, guys, take out a piece of paper. I suggest we're going to be doing the very first thing in that course outline. Take out a sheet of paper. In other words, I don't care if you do it on graph paper and all that. This is heading number 1. This is the geometry for your ground floor, okay? And basically what I expect you to do is on your piece of paper is put geometry for ground floor, and therefore, now, you notice here that this is the size of the house, 27 feet 9 inches on one side, 42 feet on the other side, okay? Now, normally, let's talk about this, okay? Normally, this is your foundation wall here, okay? Everybody knows what a foundation wall is, okay? So this is your foundation wall. And normally your foundation wall is also gonna be supporting your wood structure, or it's going to be supporting most of your wood structure. So therefore you can consider this to be a supporting element, okay? Now, I'm going to repeat this, and I've mentioned this a number of times with you guys, okay, is that in any design, okay, the first thing you have to establish is geometry. It's not your loads, it's not anything else, is your geometry. So the first thing you have to decide is, where am I going to place my columns? Where am I going to be placing my beams? Where am I going to be placing my joists? How am I going to divide this space, okay? Now, it also depends on the architect, okay? The architect might tell you, I don't want to have no beams, no columns in the basement, okay? He can say that, right? Then all of a sudden you're stuck with a 27-foot 9-inch span here, or a 42-foot span there. So, that becomes ridiculous, especially if these are homes that are going to be built at a modest cost, okay? So now, When it comes to wood, okay, and you're going to be framing with lumber. Lumber means that it's, you know, being cut from a tree, okay? Lumber comes in, we'll talk about this next week. Lumber comes in specific lengths. Does anybody know the length of lumber?
8 feet.
That's the minimum. And then what?
I assume 12.
It goes up in multiples of 2 feet. You can get 8-foot lumber, you can have 10-foot lumber, 12-foot lumber, 14-foot lumber, and 16-foot lumber, okay? You can also have 20-foot lumber, but it's not readily available in the lumber yard, okay? So normally lumber, if you guys ever go to a lumber, like if you go to a rental depot, if you go to Home Depot and you walk around the lumber rack aisles, okay? You know, you get an idea. So normally what you look at is that I'm going to be using lumber for my joists, okay? And normally my joists go from anywhere from 8 feet length to 16 feet length, okay? So basically when you're looking at spanning your lumber, okay, you should not exceed 16 feet. Okay, because that's the most readily available lumber. 16 feet should be your maximum, okay? And 8 feet should be not necessarily minimum, but in other words, so these are the spans of your joists, okay? So right now, I have 27 feet 9 inches here, okay? So that means that, well, I know that I can't, there's no way in hell I can use a 16-foot joist here because it's not going to get supported by the other side of the foundation wall. So what do I have to do in between these two?
Put a beam.
Okay, so that's right. So in other words, I would put a beam down the middle, okay? And therefore, I know that by putting a beam down the middle, this will be less than 16 feet. This will be less than 16 feet, and therefore, I can easily get in there with lumber either 8, 10, 12, 14 feet, okay? So that's what I mean by creating geometry. So the first thing you have to do is decide where you're going to be putting your supporting elements. So this is going to be a supporting element, my foundation wall. This is going to be a supporting element, my foundation wall. And then I'm going to be putting a beam down the middle, okay? So that's the first step, okay? Now, so we all agree that we need a beam down the middle. So let me clear this. So let me just, so there's my beam. Sounds good, okay? Now, this is my beam. And that means that my beam will be running across here. Now, I don't worry about the span of the beam right now. I'm not there yet. I'm just going to be worrying about my floor joists. But I know that this will be my beam that will run right across the middle of the of the floor here. Okay, and of course, I will be putting it, you know, right down the middle. So in other words, so what is that? What does this mean? That this becomes 4.32 will become what does this represent? 4.32.
The span of the joist?
Exactly. So in other words, when you're doing the calculation for your joist, your L now becomes 4.23 meters. That becomes the span for your joist, okay? And that means that your joist will be put in this direction, okay? And they'll go from here all the way down there. In this direction from here. And then don't worry about the openings now. We'll talk about the openings in one of the labs, okay? So this is basically how you're going to be spanning your joists, okay? Now, what you're going to do, we're going to be designing our joist next week, but this is basically the first geometry you worked out. So you've already worked out the geometry of your floor. You're going to be putting a beam down the middle. Where are the columns going to go? Well, when we get to built up beams, we'll worry about that. Don't worry about that now. But we know that we'll have a beam going down the middle and that our floor joists, okay? See, I know there's 14-foot joists, so I don't have much weight. First of all, it's good that I have 14-foot joists, so therefore I can order 14-foot joists, and I'll have very little waste, and I'll be able to span very nicely in this direction. Now, if for whatever reason, if you wanted to, okay, you can also look at, you know, if you wanted to, you can also look at putting beams in this direction, okay, if you wanted to. And then span it. See, so it's up to you. But I think this is probably, you know, like whatever. So, but what I'm saying is that the first thing you have to worry is work out some kind of geometry so that you can start, you know, clear. all the drawings. Okay, so now
what is the biggest size of joist that we can get?
if you, it's like Rena, if you're looking at floor joists, okay, like we'll talk about sizes next week, okay, but if you're looking at floor joists, like you're talking about lengths or sizes?
The length.
The length, okay. Typical length for floor joists minimum is 8 feet, okay, and typical long length is 16 feet. This is what the lumberyard carries, you understand? That's the longest. Now you can get 20 feet lumber, but it's special order. You might wait 8 months for it. You follow? So you never start. You understand? Now, so when you talk about lumber, you're looking at anywhere between 8, and then after that, it's 8 feet. Then it goes in multiples of 2 feet, or 10 feet, 12 feet, 14 feet, and then 16 feet. Okay. So those are the typical lengths: 8, 10, 12, 14, 16 that the lumber yard will carry. And if you want, you can go, you won't find anything less than 8 feet. That's for sure. Okay. And if it is, it's scrap wood. They don't sell anything less than 8 feet. So those are the standard lengths. Okay. Is that clear, Rena?
Yes. Thank you.
Okay. Okay.
Sir?
Yes.
Is there a reason why your joists are not on the same, like they're not the same?
I'm sorry. Is there a reason why my joists aren't what?
The same, like they're not in how can I say it? They're not together.
Oh no, I just did them to represent joists. I mean.
Oh, okay.
In other words,
okay,
like
I thought there was a reason.
Okay, I just did that to represent joists, so that you can see that I will have a set of joists in this bay. You understand?
Yeah.
And I'll have a set of joists in this bay. You understand? That's why I did it. But when you're actually building it, Adriano, you're absolutely right. The joist would go here like this, right?
Yeah.
And then the one next to it will go right next to it like that. You understand? You're absolutely right. That's how it's going to actually, you'll see that on the drawing, understand? But this is just to represent that I'll have one series of joists here and I'll have another series of joists there, okay?
Okay, perfect.
But when you're actually going to build it, this is what you're going to see. You're absolutely right, okay? Okay, so that's the geometry. So that's what I expect to see in your design brief. Like in other words, a nice plan view showing me the outside dimensions, where you're planning to put your beam, what is the span of the beam. In other words, just copy what you see right here and have that in your design brief. Because you're gonna have to come back to this,
Sir?
Yes.
So I know you just said it, but like, do we have to choose our like numbers, or we can just use the same number? Like, I'm not even sure what we're doing. I copied everything.
Exactly. That's what I wanted you to do. Copy this. Perfect.
Okay, cool.
In other words, perfect. In other words, that's exactly what I want you to have. I want you to have this in your design brief. And what I'm stressing here, Omar, is that you're starting to realize that the first thing you have to establish if you want to design anything is what? Because like textbook examples, they give you the span, they give you the loads, and they ask you to do the calculations, and then they expect you to come up with the design, right? But in real life, like you have to create your spans, you have to create your geometry. You understand? You have to determine your loads.
Yeah. Okay.
See? So this is what I'm trying to make you understand is that, remember that architectural plan that you had at the beginning? Well, that's all you see in real life. That's what you receive from the architect, and he says, okay, give me the wood structure for my building. And he expects you to develop this. He's not going to tell you where the beams are. He's not going to tell you where the columns are. You're going to tell him where the beams are. You're going to tell him where the columns are. And if all of a sudden he doesn't want the column there for whatever reason, then you're going to have to work out another solution. Understand? Yeah. So, okay. So this here is basically, so we all agree that this is how we're going to lay out the floor structure. We're going to have a beam going down the middle, and we're going to have a floor joist spanning from the foundation wall here to the beam, and from the beam to the foundation wall. Okay. Okay. Now, the next thing is, of course, now that I've got my geometry, what's the next thing I have to determine? Of course, now I got to determine my loads, right? So now we have to determine the dead load for a floor, right? Now, normally, if an architect was involved, he would send you a little detail on his drawing called a floor assembly. Okay, he will tell you how he's planning to construct the floor. Okay, so for example, here I fictitiously came up with a floor assembly, which is typical for this quality of home. Okay, so here the floor assembly, we're going to assume that it has 3/4 inch hardwood floor. Okay, it's going to have 5/8 inch tongue and groove plywood subfloor. We just determined that that was sufficient for our load from the table. And then of course it's going to have the self weight of the joist. Now here what I'm going to do is I don't know the weight of the joist yet. Okay, so what I'm going to do is I'm just going to assume one, and then I'm going to check to make sure I made the right assumption. So I'm going to assume that the 2x12s at 16-inch spacing. Okay, and if I end up with 2x10s at 16-inch spacing, all the better. That means I've overestimated the weight of my floor joist, and I don't care. So that's something I have to assume at this point here, and I will eventually confirm that assumption is good. Then of course I have a 1/2 inch gypsum attached to the underside of the floor because it's going to be a finished basement. And what I need to do in this case is that I'm going to be having partitions sitting on my floor. Now, I can either go back and design each partition resting specifically on one joist, or I can make an allowance for the partition. So this way, no matter where they happen to fall, I know that I've kind of allowed for that in my design. Now, here, since it's residential, okay, I tell you that I'll use about 10 pounds per square foot for my partition of residential. Now, if this was an office building, the National Building Code requires you to make an allowance of 1 kPa. Keep that in mind. This is just me making a reasonable allowance for residential, okay? But if this was a office building, the building code requires 1 kPa minimum for your partitions, okay? That would be 20 pounds per square foot. So now, so here with, now, of course, if you guys must have seen this. Did you guys see this table ever see this table before?
Yes.
Yes.
Okay.
Instructional.
Yeah, exactly. Okay, so this is where you come and you select the design loads, okay? Do you guys still have a copy of this table, or do you want me to send you one by Leah?
Can you send this one, please?
Send this one, please.
Yeah, I'll send you one by Leah, okay? So I'll send you one for Leah. And so this is the table where you go and get all your, you estimate your floor finishes and all that, right? So I'll send you one by Leah right after the lab. Don't worry about it. Last viewed. Okay, so here what I want you to do is, of course, what you normally do, like this is what I do, is whenever the architect sent me anything, I would like to take a direction. I always like to start on top, work my way down, okay? And if I'm doing a wall, I start from the outside face, work my way in, it doesn't matter. But I, systematically list how each element is being built up in the assembly, okay? So I list them all here. And now here, I expect you to go find a value from that table, put it in here. I expect you to go find a value here, and I expect you to go find a value here, and I expect you to go find a value here. And then I can tell you that if you do this correctly, it should come out to 0.99 kPa, okay? And that should be the weight of your floor. So in other words, we're not going to use 0.99, we're going to round it up to 1 kPa. So in our project, we are always going to be using 1 kPa to design our floor, and the same dead load to design the beam, okay? So this is the dead load that I expect to see in your, like, in other words, you know, you guys, do you want a copy of this lab also through Leah? Or do you guys want me to, or you're gonna be able to get it through the video? You should be able to get it through the video. Okay.
Are the videos gonna be posted on stream?
Yes. Like right after, 9 times out of 10, if not 99 times out of 100, I always try to, first I has to convert into a video, and then I stream it. It takes me about an hour and a half, but I try to send it right after the day that we finish the lecture, okay?
Carmelo was using Teams.
Sorry?
Carmelo?
Yes.
He was using Teams to share the videos. So I don't know if that's easier for you too, or.
I don't understand what you're asking, what you're saying though.
I said that Carmelo, he's using Teams, like the application Teams, instead of the stream to share the videos.
Oh, okay. Well, look, that's
So
what
I
he
don't know,
does.
that's
Like,
easier or not.
Last year, you guys were getting the videos through Stream. I sent you the link. Was that a problem?
No, I was just maybe thinking it was easier. I don't know.
I mean, I find that to me it's very simple. I stream it through Microsoft Stream. It gives me the link, and I send you the link, and that's it. And then you just you open the link and you get the video. I don't think there could be anything easier than that. And especially what I'm going to do this year to make sure that, because normally what happens is that I'm going to add you guys as a group to the video. So therefore, if you happen to open it up with another email or whatever, as long as you're opening up with your email, you should be able to open it up anywhere. Understand? So sometimes people when they're streaming, they don't realize that they have to give permission to the people that can actually open up the link. Okay. Anyway, so don't worry about that. That's going to be me. You're going to get the link, and I think that that's the easiest thing to do. I send the link through Leah. You get the link, and I even put it on a separate category. Very easy to follow. I don't think you should have a problem. Okay, so here is what you're going to, of course, have in your design brief. Okay, and you should come out with 0.99 here. And of course, like when nobody uses 0.99 in real life, you round it up to 1 kPa. So that's going to be the dead load for our floor. And now for the live load, okay? Now the live load, okay, this is, of course, the National Building Code determines the minimum live load you should be using depending on the occupancy, okay? So the National Building Code of Canada requires that the live load shall not be less than the values listed in this table. So if you open up the National Building Code, no matter what year, this is the table that you find in other words, it's under part 4, the first section, table 5.3. And therefore, this is okay. So this is what you see in the National Building Code. So in other words, it tells you depending on what the room is going to be used for, if it's going to be used for, like an assembly type area, in other words, where you can have, for example, dance floors, dining areas, foyers, you should be using 4.8 kPa. Classrooms and courtrooms without fixed seats, 2.4, okay. So this is what I was telling you, like a school, all of Dawson, all the floors in Dawson, I'm talking about the classrooms now, were designed for 2.4 kPa, okay? So this is where you come and you see what's the minimum live load you should be putting, on your, for your design. And of course, you get this from the National Building Code. And of course, what we're gonna do is, okay, we're just gonna come here and we're gonna look for residential, okay? So here, residential, you go down and it says here, residential areas within the scope of article, which is sleeping and living quarters in apartments, hotels, motels, boarding schools, and colleges. So the live load that you designed for is 1.9 kPa. And in my days, that used to be 40 pounds per square foot, okay? As a matter of fact, in my days, way back when, you used to have bedrooms were designed for 1.3 kPa and the other area of the house was 1.9 kPa. And it was 30 and 40 pounds per square foot. Now they rounded all that up to 40 pounds per square foot. So here's the live load that we're going to be using to design our floor, our beams, our columns, and everything else, okay? And like I said, so see here, this is where I was telling you about the roof, the minimum 1 kPa for the roof. This is where, the live load for roofs. So if you're ever calculating snow load and your snow load happens to be less than 1 kPa, remember you have to have at least 1 kPa. You shouldn't totally disregard. Okay, and that's it. So that's where we get our live load from. So therefore, we're going to be using 1.9 kPa. And that's it. So what I'm going to do is I'm going to send you a copy of that table where you have the materials. Let me just stop sharing here. I mean, stop the, yes, hold on.
Yep.
Okay. Stop sharing. I'm going to pause the recording because this way it's going to be